Hey, this is the 16th episode of Advanced J1939. In this episode, we'll continue more with termination, which we covered the theory of in the previous episode. So I have here a 250K CAN bus. This is a network with several controllers on it. There's about 20 feet or about 7 meters of J1939-15 twisted pair unshielded cable. So if we take a look at this, this is a 250K CAN bus. This is a message PGNF003 from an engine controller, which is source address 0. If we take a look at, let's take a look at here at the first. I want to kind of show this first because we're going to look at this later. We're going to see this. It's going to, this is hopefully make some sense later on when we discuss this. If I look at this first start of frame, so this has an ID or a priority of 3, so this is a pretty high priority message. If we look at the start of frame, we know the start of frame bit always has to be a dominant. So we then have a dominant bit right after it, which is the first bit of the priority. So this being 3, which is in this case a 0, 1, 1 in binary. So if we also look at the difference in time, this is approximately, should be about 8 microseconds. So this is a 250K CAN bus. So the time for these two bits together, the start of frame plus the ID, the priority, we see that this is, so arbitration, as we talked about before, this would probably win arbitration in most times. Priority 3 is pretty high. 0 is the highest priority. That would be something like torque speed control or TSC1. Maybe we'll talk about that one of these days. But if we see this is a set of 250K CAN network, so 4 microseconds per bit. We'll go ahead and zoom in on this pretty close as well too. Let's take a look. Actually, let's do this instead. I'll go ahead and we'll let this run. I wanted to show this, so let's go ahead and let this run. And I'm going to go ahead and just change the time base here, and we'll get zoom in so we can take a look at, and let's get rid of our markers, our rulers, don't need those. If we look at this, just trying to look at one bit. And so I'm going to drag the trigger for this. We'll drag it over this way. I've got it so it's a falling edge trigger. If you know anything on scopes, you know that what we're looking for is when the edge of this for channel A drops below this value, then we're going to trigger on that. So this is pretty well damped. We can see that there's termination on this. As we talked about in the theory, this is never an exact straight vertical line. There has to be some slope to it. I'm taking 10 million samples per second, and we have 2 microseconds per division. So each one of these divisions is 2 microseconds. So 2 of these divisions make up 1 bit at 250K, right, for 4 microseconds. So the important thing I wanted to show here with this network, which is about 20 feet with a 120 ohm passive terminator, which means it's just a plain old regular resistor, 120 ohm at either end of the network. So if I were to remove one of those resistors, but before I do that, let me go ahead and pause this, and let's drag a ruler down and let's get an idea of what what the height of this, or excuse me, the voltage, the amplitude of this is. So let's take a look at both CAN high and CAN low. So we have them. I'm going to go ahead and I'm going to remove one of the terminating resistors off of this network, and let's take a look at what happens. Not a lot is probably going to happen. So we can see that a couple of things occurred. This network is still working fine. The one thing that did happen is the voltage has increased slightly, and the difference in voltage, and so the CAN low actually goes more negative direction. So we actually end up with a greater difference in voltage because we've reduced the impedance, or we've reduced the load of the network. So instead of being 60 ohms that the CAN transceiver is driving into whenever it's communicating, it's now driving into 120 ohms. So I've reduced that resistance. And so because I've reduced that resistance, I'm dropping less voltage on internal components in the CAN transceiver. That means it's going to get dropped out onto the CAN bus. I don't know, some people feel that they can look at CAN voltages with a DC multimeter and can pretty much diagnose CAN network with a DC multimeter. Okay. I've never been able to do that. I mean, I can find shorts and opens, but yeah, trying to see this difference in, this didn't change very much, and so the average voltage of this, the mean voltage, would change by very little because of this loss of termination. So we're going to let this run again, and we'll take a look. If you notice, you didn't see much of a change in the slope of this, so it looks a little different. I'll go ahead and plug it back in one more time. So we'll plug back in the terminator. It really doesn't change much. You can see the voltage decreased because we're now driving into 60 ohms instead of 120. 220 is in parallel. There, I took it back off again. There's a slight change in that ramp, and it's not much at all. So it really, and as I talked about in the theory, we got to make sure that we can get back to the recessive state as quick as we can. So we went from the dominant state to the recessive state. We've got to make that change quickly. I can't have a long decay. So let's go ahead, and we'll go ahead and run this again. And hopefully there we go. Okay, got this running. We'll go ahead and drag this over just a little bit further because you're going to see what's going to happen when I remove the second terminating resistor. So I'm going to make this network run with try to run with no termination. And there we go. We'll go ahead and let's change the time base a little bit just so that we can get a better look here. So now I've got 5 microseconds per division. A couple of things occurred, not that it's real important. The voltage increased, right? Now I'm driving, I'm basically driving into only the other CAN transceivers that are out on the network. So this voltage increased. You can see the thing that's happened here, and this is what I wanted to show with the 8 microseconds of bits in the beginning. So let's go ahead and pause this, where we have at the start of frame, and we also have a message with a high priority, with a priority of 3. So here's my 8 microseconds. So there's that same controller, the engine controller. More than likely, I don't think there's anything else that's on the CAN bus that's trying to transmit anything with that high priority. We can see that there's my 8 microseconds, probably the engine controller. I can't tell what it is because it's given up arbitration. And the reason it gave up arbitration is because of this loss of termination. As I told you, as I mentioned in the other, about going from dominant to recessive, it's about half a volt. So this won't be considered a recessive bit, even though it's way out here, it becomes a recessive bit. And this is this decay because there's so little impedance, there's so little resistance out there to discharge this capacitance of the network. There's no capacitors on this network. It's just wire, just twisted wire with insulation on it, which is a capacitor by definition. So it's the wire, the copper is a conductor. It's a plate of a capacitor. The plastic insulation, or whatever it's made of, is a dielectric or an insulator, and that is a capacitor by definition. So we got a pretty good amount of capacitance on this wire. So if we look at this, the reason that this is occurring, and let's go ahead and I'll zoom out and we'll take a look at. Let's go ahead and start again. We'll look at this at a different time base. Let's go ahead and increase this way on out, and let's get rid of our rulers. We don't need those anymore. What's occurring on the network is no controller is communicating. This is a dead network. And the reason it's dead is because this is more than likely, this is the engine controller or whichever controller it would be, trying to put a message out onto the CAN bus, and it's giving up arbitration, or it feels that it's lost arbitration because it is detecting that it is, even though it's driving to a recessive state, it's trying to drive its transistors to a recessive state, it is being detected as being a dominant state. Therefore, it stops communicating because it believes it lost communication. Over here, it's like, oh, the network went back quiet again. It's got its sufficient time. I'm going to try again. You can see that's all that is occurring here. This network right now is just basically garbage. I said, if I looked at this with a multimeter, I don't know what I would see for a voltage. Probably something where you would say it looks normal and looks okay. But this network is definitely not okay. Okay, so I'm zoomed back in. We're taking a look at this with no termination. This is about 20 feet of J1939 cable. I'm going to go ahead and I'm going to plug in another 20 feet of cable. So this is going to increase the length of the bus to 40 feet. So if we look at this now, it's increased the capacitance, and because of that we can see that this decay time is even longer. So this looks like the simulations that I showed you in the previous episode. This is even worse now. By increasing the length of this, I've increased the capacitance. This is one of the reasons that there's a limit on how long the CAN network is supposed to be per the specification. It depends on whether it's J1939 11 or whether 15, whether it's twisted shielded or twisted unshielded. In practice, a lot of manufacturers don't follow any of that. They just make it as long as they have to make it. And I myself, as a test engineer in the past, there's been plenty of times that I've put another 50 feet of CAN network on because I had something in a cold cell or something, a cold chamber, a truck or machine, and I needed CAN information, I needed it outside of it. And so, yes, I violated the standard, but I know I'm what you call an expert, right? So I knew that it wasn't causing a problem, and I could scope it and I could see that it was well within the fault time that we needed. So I'm going to go ahead and plug one of the terminating resistors back in with this 40 feet of cable now. And we can see just with one terminating resistor, the network is back up and running and working. So here we are. Everything looks fine now. There is a longer decay now with the 40 feet versus the 20 with the one terminator. I'm going to go ahead and put the other terminator back on. And when we do, you probably didn't see much change at all if we don't see anything. This is what it looks like now with the 40 feet of cable. So our decay looks fine. So this CAN network is up and running again. One other thing I probably need to add, I've mentioned that these 120 ohm resistors, just plain resistors, are what we would call passive termination. And by passive, it means that there is no electronic components within it. It only contains resistors, capacitors, and inductors. So that would be a passive device. Something that is an active device would contain have something which would have voltage regulation, would have other electronic components within it. So there is something that is also referred to as a terminating bias circuit, or a TBC. These are perhaps called an active terminator by some manufacturers. I'm probably not going to cover anything with active termination for a couple of reasons. For one, I don't know, other than perhaps with ag for maybe for the ISO bus or the implement bus, if active termination is still in use. I think it has been phased out. Basically, active termination, instead of having 120 ohm terminators, we have active components which are so electronic components which try to hold the CAN bus, CAN high and CAN low, at 2.5 volts, and would have resistors in series. So I don't have a schematic for a device that I could show you. And there's not much that's out there on active termination. I'll just leave active termination up to the manufacturers to discuss. As I indicated, I think it's kind of something becoming something more of the past. I don't know. I mean, let me know, put it in the notes. Besides perhaps the ISO bus, I don't know that any manufacturers use active termination on their CAN networks any longer. I think it's been phased out over the last few years. So this is termination. This is the passive termination. And to review, the reason that it's there for is for this decay time, so that we can pull from a dominant bit down to a recessive bit very quickly. I need to be able to